Every stress map on this plate, even the shear, was reconstructed from a camera that measures one number per pixel. In this article, the full in-plane stress tensor power spectral density of a basic-sided structure was identified from a single invariant thermoelastic camera measurement. Fatigue prediction needs this full matrix everywhere, yet strain gauges are pointwise measurements and finite element stress is computed, not measured. So what is thermoelasticity? Squeeze a piece of metal and it warms slightly, stretch it and it cools. The effect is tiny and perfectly reversible. Hold the load still and the warmth leaks away by conduction, so a static picture shows nothing. Cycle faster than about 5 Hz and conduction cannot keep up, so temperature tracks stress as a clean wave. That millikelvin ripple is exactly what an infrared camera can read, pixel by pixel. Each pixel collapses to one scalar, sigma xx plus sigma yy, and the shear never enters it. Within each mode, the ratios between the stress components are fixed structural properties, independent of excitation. Step 1. Characterization. This step is done with the shaker off. A modal hammer taps 6 points on the back, while the camera films the painted front. System-equivalent modal mixing replaces the model's invariant with the camera's, and the model's physics carries that correction into every component. The hybrid inherits the measured resonances at 53.7 and 174.7 Hz. Modal identification then delivers stress mode shapes carrying all 4 stress fields, with the ratios locked in. Step 2. Broadband random base excitation. While the camera records and one base accelerometer is the reference. At every pixel, the H1 transmissibility to base acceleration rejects the camera noise that is uncorrelated with the shaking. Projected onto the 2-mode shapes, 1,156 pixels collapse into 2 participation factors. The same 2 factors, expanded through each mode's fixed ratios, synthesize every component, even the shear the camera never measured. Scaled by the base acceleration spectrum, the opening maps are earned, the full 3x3 matrix, cross-spectra included. Against an exact numerical reference, the component amplitudes are recovered to roughly 11% and von Mises to 5. Fed through a Dirlich estimator, the recovered spectrum reproduces the exact fatigue damage within 6%. Every pixel acts as a virtual strain gauge rosette, 1,156 of them, a density no contact sensor could match. The invariant is measured. The components are reconstructed through an experimentally corrected modal expansion for thin, isotropic, metallic plates. Published in Mechanical Systems and Signal Processing. The code and data are freely available online.